All right, let's do this. Let's finish our discussion of gases. The first thing that we're going to do is define what is called standard. This is going to drive me nuts. Give me one second. All right, sorry. Standard temperature and pressure. Or STP. All right, so this was just this like standardization of conditions for which we can talk about gases. Of course, you can carry out reactions outside of standard temperature and pressure, but it just kind of is nice to be able to compare. If we all do our experiments under the same conditions, then we can really compare our results a lot more easily. So standard temperature and pressure is just a specific temperature and a specific pressure. So a temperature of exactly 0 degrees Celsius and a pressure of exactly 1 atm. Okay, so let's take our ideal gas law and figure out the volume of 1 mole of gas at STP. And we'll say of exactly 1 mole of an ideal gas at STP. All right, so everybody take a second based on what we discussed last class with the ideal gas law and these new conditions here, standard temperature and pressure. Tell me what the volume of a gas is at STP. So if I take my ideal gas law and rearrange it, I get volume equals nRT over P. Okay. I'm going to plug in my N is 1, actually just 1 mole exactly, times that value of R, that 0.082058. And that's on our constants page. You don't have to have that memorized. And then times my temperature, so 0 degrees Celsius, right? Boom, yeah, no, you can't use Celsius in this equation here. You would actually have found that the volume would be 0. Well, that doesn't make any sense. All right, so yes, we got to convert to Kelvin here. Because we're at exactly 0, it's just that 273.15 number. And then I'm going to divide that by my pressure in 1 atm. All right, punch that into my calculator. That is 22.41414. Our units will work out where ATMs cross out, moles cross out, Kelvin crosses out, and so I'm left with units of volume, or 22.41414 liters. Sorry, this thing's about to die. All right, so this number, especially just arbitrarily rounded here, 22.4, is a value that you often hear associated with 1 mole of gas, right? 1 mole of gas occupies 22.4 liters, which is about the size of like a beach ball, okay? And that's a really good kind of mental picture to have as to how much space a mole of gas occupies, but it's important to keep in mind that is only at one specific temperature and one specific pressure, right? If we were to change the temperature, raise it to room temperature, that gas would expand a little bit. Or if we were to increase the pressure, that gas would contract a little bit. So it's kind of a good, helpful rule of thumb, but it's not a number you want to get married to, right? You see it's sometimes used as like a conversion factor. You definitely don't want to do it like that. We always want to use our ideal gas law, which will account for temperature and pressure. Okay. Actually, if I was being good, I'm limited here not by my moles, temperature, or pressure, because those are all exact, but by my 5 sig figs in that value I looked up for my ideal gas constant R. Cool. All right. So now we're going to introduce what's called kinetic molecular theory. Okay. One of the reasons why gases are kind of like held up as like a good example of chemists' ability to describe substances is because all of these theories of gases that were laid out way back in the day, right, like the 1700s, all these observations that were made, it turns out that you can take more complicated physics and you can derive that exact same expression that we got, our ideal gas law. All right, and so that's what this is here, your kinetic molecular theory. This is how you derive the ideal gas law from basic physics. All right, and it's really not too crazy here, but we're not going to do the whole full derivation. We'll kind of do some highlights, but importantly, this whole theory is based on a few assumptions about gases. Right, or rather, you got to kind of start from these assumptions in order to be able to develop that mathematical theory that you end up with the ideal gas law. All right, so first of all, there are a few that are great. They turn out to be spot on here. And the first is that kinetic energy is proportional to temperature. All right, kinetic energy of those gas particles, how much energy they have just by virtue of bouncing around inside whatever canister they're kept in, is going to be proportional to the temperature of that gas. So we can kind of state this mathematically by using our fancy symbology. Kinetic energy is proportional to temperature. All right, and then we want to make note that our kinetic energy is going to be proportional to mass times volume squared. Not volume, sorry. I always want to say volume, but really here, since it's physics, it's velocity. Is proportional to our temperature. All right, so then according to this here, if I increase the temperature, what is that going to do to the speed of those gas molecules? It's going to increase them, right? So by increasing temperature, what you're really doing is speeding up just how fast those gas molecules are zipping around inside whatever sample you have. Cool. Our next one is that the gas particles are always in random motion. Right? There's not like synchronized swimming across that vessel where they're all kind of moving in unison and in the same direction or anything like that. They're all behaving independently, all randomly bouncing around. okay? And again, totally true, right? Nothing wrong with that. But then there are a few assumptions in this kinetic molecular theory that are not so great, all right? So the first one is that gas particles occupy 0 volume. All right, and by that I mean the particles themselves. All right, so what this assumption is saying is, like, if we take a sample of argon gas, that argon atom itself isn't occupying any space. And that's not exactly true, right? Those protons, those electrons, they do occupy space. We talked about the radius of these things. Going down, they even occupy more space, right? So anyways, this is this sort of assumption that this theory makes, and it simplifies the math like a ridiculous amount, but it is a bit of a lie. All right, now you can get away with it because in a gas particles are so far apart from one another that, you know, their size is not really all that important. Most of the space in this room is empty space. The actual space occupied by the oxygen and the nitrogen is not very good, or not very much, right? So on assumption, it's not 100% true, but it's pretty good. All right, so we're going to put a little asterisk next to that one. Not totally true. All right. The next one is that all collisions between gas particles are perfectly elastic. Okay? And this term elastic has a very specific meaning in physics. It means that no kinetic energy is lost. Right? So this is a type of collision where these two particles have the exact amount of kinetic energy when they smack into each other as they do when they're flying away. Okay? So importantly, what it would mean to be inelastic. This means that the particles stick together a little when they collide. All right, so if we took, for example, billiard balls and we rolled them into one another, that's a good example of an elastic collision. Those things hit each other and they just bounce off in the same direction. There's no loss of kinetic energy in that system, okay? If we took a big wad of chewing gum and we threw it up against the wall here and it sticks to it, that is not an elastic collision. It didn't bounce right back off, it's stuck, right? And so that would be an inelastic collision there. And of course there's some in between. Maybe if we threw it hard enough, it does bounce a little bit, but not as much as it would if it was a billiard ball, for example. All right, so in an inelastic collision, some of that kinetic energy is lost during the course of that collision because there's this interaction between those particles. And so what our assumption is saying is that if these collisions are elastic, that assumes no intermolecular interactions. All right, in order for these gas particles to truly behave like billiard balls, they can't interact with one another at all when they collide, okay? And what did we learn about compounds? Do they have, about molecules? Do they have intermolecular interactions with their neighbors? Yeah, that's why we got a name for it here, right? And we talked about the different types, the dispersion forces, the dipole-dipole, the hydrogen bonding, right? There's a whole bunch of ways in which particles interact with one another. So again, this is one of these assumptions that we're going to put a little asterisk next to because it's not completely true. Gas particles do, in fact, interact with one another. But for the sake of this theory, right, this sort of derivation of the ideal gas law only works if you assume those collisions are perfectly elastic. And again, it's an assumption, and it's not completely true, but it's not all that bad of an assumption. Most gases are very nonpolar molecules. They don't interact with one another very strongly at all. So even though there are some intermolecular interactions, they're very weak. And gas molecules spend most of their time in this empty space. They only collide with one another every so often, right? So again, not perfectly true, but not the worst assumption in the world. Cool. So it turns out that if you start with just these four assumptions here, you can derive the ideal gas law. All right, and we're not going to do the whole thing, but we're going to point out the highlights here by just starting with that definition of pressure. Right? We said that pressure was the force with which particles collide with the walls of the container per unit area. All right, and so basically through some fancy physics, you can show that this has to be proportional to the kinetic energy of those particles times what's called the particle density. And this comes up a lot in this theory, this particular quantity, so it's kind of interesting to just note. They gave it a special name. It's just number of moles divided by volume. But within the theory itself, it plays this important role. It's the density of that gas, right? How many moles of gas, how many particles are there per unit volume? This times the area is all equal to the force, and then you get to divide it by the area. So that cancels out. And what did we say that this kinetic energy term was proportional to? Yeah, it was one of our first assumptions here in our kinetic molecular theory is that it's proportional to the temperature of that gas. So what we just sort of said is that, all right, if we're going to trust this physics here, that means that pressure is proportional to temperature times this particle density here. And remember, what it means to be proportional to is that the pressure is equal to some constant times temperature times number of moles divided by V. And what do we call this constant in our ideal gas law? What do we use variable-wise? Yeah, the R, right? So what is that R? That's our proportionality constant that we need here. So when we have our ideal gas constant, all you can see here is if you rearrange this, this is just our PV equals nRT. All right, and so you can sort of derive this ideal gas law by starting with those four assumptions in our kinetic molecular theory. All right, so what we say is an ideal gas is a gas that occupies no volume at all and that doesn't have any interactions with its neighbors. All right, because that's what we need according to our theory here. So an ideal gas, no volume, no interactions. All right, so no gas is truly an ideal gas then, because all gases have some volume associated with them, as well as they have some interactions between neighboring particles. All right. If we look at our periodic table here, which one do we think is the most ideal out of all of the gases? Yeah, so our noble gases are great sort of ideal-ish gases because they don't have very strong interactions with their neighbors. They're just single atoms, right? They don't like interacting with other things that are already happy. And helium being the smallest up there, yes. So the smaller we get on our periodic table, the more ideal we get, as well as if we don't have any of those strong intermolecular interactions. Cool. All right, so there were a few other things that the, big brains in the physics department do, right? Theoretical physicists just sit there with pencil and paper all day and do math, and then they come up with cool crap, and then we go into the lab and we test it out. So they came up with this theory here, this kinetic molecular theory. They derived the ideal gas law. That was pretty cool. Again, matched with what those old Boyle and Charles and Avogadro scientists were already saying. And then there were a few other things that kind of fell out of this theory here that they were able to test and was pretty spot on. So the first regards the average velocity of gas particles. Okay, and truthfully, I'm lying to you by calling it the average. Mathematically speaking, it's really called the root mean square. But we don't have to complicate things too much, all right? So this root mean square velocity here, you can sort of use this same theory to show that it's equal to 3RT over the molar mass of that gas. Okay? Since if we have a gas, let's say we have a mixture of something like helium and something like xenon, one really small gas molecule and one really large gas molecule. Well, according to this theory here, if they're both at the same temperature, they have to have the same kinetic energy. But one of them, if we look at our equation for kinetic energy, right, mv squared, one of them has a way larger mass, so then it must have a slower velocity, right, if their kinetic energy is going to be the same. Likewise, helium would have a really small mass, so that means it needs to be moving around very fast to have the same kinetic energy as those xenon molecules. All right, so that's why we see this inverse relationship with molar mass here. All right, this is just the average velocity. Really, if we looked at a sample of gas, all of those molecules wouldn't be moving around at the exact same velocity. All right, they would just have, on average, the same kinetic energy. All right, so if we looked at, for example, velocity and number of particles, okay, what we're going to see is our root mean square velocity for something teeny tiny like helium is going to be much larger than our root mean velocity for something really large like xenon. Okay? The distribution here, though, as these particles start moving around faster, their distribution of velocity actually spreads out as well. So this curve, even though the center point here is higher up on our graph, it's also a lot squatter and flatter, whereas the other one has a much more sort of narrow shape to it. All right, but importantly, our average point here, or not quite the average, but the root mean square, is larger for helium than it is for xenon. All right, the other thing that this equation shows us is that their velocity depends on the temperature. We kind of talked about this already. So if I increase the temperature of a gas, all right, so actually let's just title this little graph here. This is if we increase molar mass, we decrease our root mean square velocity. Now we're going to make another little chart here. But this time we're going to increase the temperature. All right, I'll tell you that the distribution of velocities looks fairly similar. At one temperature, your particles are all sort of bunched around at a slow velocity. At another temperature, they're moving around faster, and that distribution is more spread out. But now I want to think about it here. Which one is the red curve and which one is the orange curve? High temperatures or low temperatures, right? So one of these curves represents the movement of these gas particles at high temperatures. The other one represents the movement of these particles at low temperatures. All right? And if we look, where is our root mean square here? So for the orange curve, we have a larger value for that root mean square than we do for that red curve. So what do we think? Orange is high temperatures or low temperatures? Are things moving around faster at high temperatures or faster at low temperatures? To be clear, right? I mean, if we look on our graph, the orange is a larger velocity than where the red is, right? So my orange curve means that those particles are moving around faster. So should faster be high temperatures or low temperatures? High temperatures, right? And if we look at our equation here, we see that this root mean square velocity is directly proportional to the square root of that temperature, as opposed to inversely proportional like it is for molar mass. So this would be our high temperatures, and this would be our low temperatures. Okay, so this idea of root mean square velocity, or we can just kind of think about it as an average velocity. We get this relationship that comes out of that kinetic molecular theory that shows that that velocity is related to the square root of temperature and the inverse root of the molar mass of a gas. All right, the next thing is diffusion and effusion. Okay, so we got a box here, and we're going to put in a partition. We're going to divide this box up into these two segments. And we are going to fill one of them with a whole bunch of gas particles. Cool? All right, so now let's think about this. We're going to take our little fancy box here, and we're going to remove that partition between those two sides. We think our system's just going to stay like this? What's going to happen? Are all of these gas molecules going to just decide to travel together to the other side? No, we're going to have them all spread themselves out evenly throughout this container. All right, and this is one of the first things we talked about with gases, but importantly comes from that kinetic molecular theory and really just the random motion of those gas particles. And this is a property we call diffusion. right? So diffusion, strictly speaking, is that these gas particles will move from regions of high concentration to low concentration. All right, but we can kind of simplify this a little bit by thinking of gas particles as gas particles will spread themselves out. To fill a container. Right? I'm not worried about like randomly walking into the hallway and passing out because there isn't any oxygen atoms over there. No. The oxygen spread itself out perfectly throughout every corner of this room, right? So the idea that gases diffuse, they will spread themselves out to fill a container, or strictly speaking, spread themselves out from areas of high concentration to areas of low concentration. All right, the other one, we're going to take our same little container here. All right, we're going to take our same little container here, but instead of removing that barrier altogether, what we're going to do is just punch a little hole in the middle of it. All right, so now we got this little pinhole here. Okay? These gas particles are all in random motion, right? So they're not all just going to start beelining it out through this hole because they're just moving around randomly. They're going to ping pong off the walls of this box, back and forth, but then eventually, every once in a while, one of them will find its way to hit that perfect spot where that pinhole is and make its way into the other side, right? And that is what we call effusion. That is the movement of gas through a pinhole into a vacuum. All right, and this would be a relatively slow process because again, these gas particles are just going to kind of randomly ping pong, and they have to hit ever so perfectly on that one wall in order to make their way into the other chamber. So because of that, because it's really just a crap random chance that they're going to hit in the right place, it's going to depend on just how fast those gas particles are moving around. Gas particles that are moving around really quickly will sample that whole box and eventually find that hole a little bit faster. If a gas particle is moving really slow, it's got much less of a chance of finding that right spot per unit time. All right, so what you can show, again, using your kinetic molecular theory, is that this rate of effusion is inversely proportional to the mass of those gas molecules. Oops, not equal, sorry. Inversely proportional. All right, so bottom line is heavier gas molecules diffuse slower than light gas molecules. Cool. All right, so these are these theories that are these, and then they experimentally tested, and indeed this turns out to be correct, right? So these are these theories that come out of our kinetic molecular theory that we can sort of test. Again, this kinetic molecular theory is just based on these 4 assumptions, 2 of which we didn't really have a problem with. Kinetic energy proportional to temperature, great. Gas particles always in random motion, great, right? But then 2 of them were a little bit iffy. The idea that gas molecules themselves occupy no volume and that those collisions are perfectly elastic. So this led a scientist to try to improve upon that ideal gas law and create what's called the real gas law. All right, and they are really cocky calling it a law because it is definitely far from a law. It is still a pretty rough approximation of gas behavior, but nonetheless, that's what they call it. All right, and so what we're going to see is we're going to try to correct for those not so true assumptions that we had in our ideal gas law. All right, so according to the ideal gas law, the volume is equal to the number of moles times R times T over P. Okay? But now what we're going to do is we're going to say, all right, but we have real gas particles, so their volume is going to be still that. We're going to start with that same basis, that nRT over P. All right, but now we know that some of that volume is actually occupied by the gas particles themselves. All right, so what we're going to do is we're going to tack on this little fudge factor here, plus, and we're going to put on this term to account for our particle volume. Okay. So this term has 2 important parts. One is this constant B. This is our volume correction. They just call it a van der Waals constant because of the scientist who named it here. All right. But this is depends on our gas. Right? So we're going to have this table where we're going to look this up, and we're going to have this correction factor here. For big gases like xenon, that correction factor is going to be big. For small gases like helium, that correction factor is going to be small. All right? But we have this little way that we're going to account for the volume of those gas particles, the volume that they actually occupy themselves. Okay? Now, in our equation here, the volume occupied by those gas particles depends on how many gas particles we have. All right, so we're also going to include that factor n, our number of moles, right? So our correction factor here that accounts for particle volume is number of moles times this constant. Cool. All right, so this kind of accounts for that first assumption in our ideal gas law that we didn't like, or in our kinetic molecular theory about the volume of the gas particles being 0. The other one that we had beef with was the idea that the collisions between gas particles are elastic. And that would account for differences in observed pressures of our gases. If those gas molecules, when they collide, are interacting with one another, sticking to one another, then they're not going to smack up against the walls of the vessel quite as hard, right? Because they've lost some kinetic energy in that process. So our ideal gas law tells us that pressure is equal to nRT over V. All right, our real pressure here, that nRT over V. And now again, we're going to add on this little fudge factor here. And this is going to account or those intermolecular interactions. All right, again, if those gas particles are sticking to one another before they bounce away, they're not going to have quite as much energy to collide with the walls of the vessel. So we're going to subtract some little fudge factor here, all right? We got another constant, another van der Waals constant here. Okay, this one is going to account, we already said this is going to account for that intermolecular forces. So this is our pressure correction. And again, just like the other one, it's going to depend on our gas. Okay? So in effect, it's going to account for the strength of those intermolecular interactions. Just how much this changes our pressure is again going to depend on how many gas molecules we have, or more specifically, how many collisions we have. All right, so we're going to see yet again that particle density. All right, and they said actually it depends on the square of the particle density. All right, now, since we already talked about our volume correction, all right, these volumes in here are our ideal volumes. So if we want to put in our corrected volumes into this equation, we're going to just rearrange what was above. And so now we're going to say that our real gas is equal to nRT minus that correction factor, minus that N, or that A. We don't have any correction for number of moles, but we're again going to correct that volume, minus NB. Okay? So what we just did for our real pressure is we just plugged in our volume correction. Right? They had those ideal volumes in our formula, so instead we're going to put in our corrected volume here. We could try to do the same thing with this one up here and plug in our corrected pressure, but I'm going to be honest, it turns into a bit of an algebraic nightmare because that pressure correction depends on volume. So you would introduce a volume variable on this other side as well. You'd have to do, it's not impossible, you could do it, but it's kind of not the algebra game I feel like we need to be playing here, all right? So we're going to just stick with our normal old pressure for our volume correction formula, and then we're going to, since we can, deck out our pressure correction formula with all of these volume corrections, all right? So the bottom line is, we're going to make it real straightforward here. Our volume correction all right, has that additional term on there. Our pressure correction we're going to deck out with everything that we can do, accounting for that real volume. Cool. All right, so these are what we want in our notes here. So let's take a look. We said we have now these two new correction factors. B, the volume correction factor, and A, our pressure correction factor, and they depend on the identity of our gas. So we have this new table here. We can ignore all this. All right. Here is a list of those constants A and B for a bunch of different gases. All right. Again, A is our pressure correction, and B is our volume correction. All right. Helium's a little bit of an outlier here. I'm kind of curious about that, but let's ignore that for 1 second, and let's take a look at these noble gases. All right, if we take a look at these volume correction factors here, we see that they're increasing as we go from neon to argon to krypton to xenon. Well, let's look at their positions on the periodic table here. It goes neon, then argon, then krypton, then xenon, right? And as we go down our periodic table, our atomic mass gets bigger. So again, our volume correction factor gets bigger, right? We have these, even these are relatively small. They're just single atoms. We could have whole compounds, whole molecules like Cl4. That has a much larger correction factor, right? So this is taking into account the size of those molecules or atoms. Let's compare two more here. Let's take neon, and now let's look at the value of A. Neon is 0.211, and then water is 5.46. And this isn't my volume correction factor, but my pressure correction factor. All right, and remember what's correcting, why you need to correct for your pressure is because of those intermolecular interactions. So why would water have so much larger of a correction factor than neon? What are the types of interactions that neighboring water molecules would have with one another? Hydrogen bonding, those very strong hydrogen bonding interactions. Whereas neighboring neon atoms would only have what? Dispersion. Okay? Now those dispersion forces, they do increase with the size of the molecule. So again, if we go back to our noble gases, we'll see that they do increase as they get bigger. All right, but nonetheless, yeah, water with its very strong hydrogen bonding interactions is going to stick to neighboring water molecules when they collide much more than neon is. All right, so let's use our table here. Let's say, what is the volume, the real volume, our corrected volume? Of 1 mole of CO2 at 25 degrees Celsius and 1.05 ATM. All right, and to be clear, we said that was nRT over P. Then we are going to add that correction factor. right, we're still talking about gases, so we still need to convert our temperature into Kelvin. Yeah, and they're just going to help you square everything away, right? So liters per mole. Oh, no, 1.05. All right, but again, now we're going to add that correction factor. Okay, so punch it all into our calculator here. And for sig figs, I'm just going to say we're going to round it to 3 here. We're going to keep it at what it would be for our ideal volume. All right, our real gas volume, 23.34326 liters. We'll say that has 3 sig figs here. All right, now, if we were to do our ideal gas volume, I didn't ask you to do this, but I did this real quick. That would be 23.30056 liters. All right, is that the exact same number? No, but rounded to our sig figs, that ideal gas assumption was pretty freaking good, right? So this gas right here is pretty close to standard conditions, pretty close to what it would be in this room right now, right? We're at about 1 atm, about 25 degrees Celsius. A mole of gas doesn't have very much deviation from ideal gas behavior, all right? Which is why in lab today, we're not going to worry about using the real gas law, making it more difficult than we need to make it in order to talk about this gas. The ideal gas law works pretty well at normal conditions, all right? Where you're going to see a lot of deviation is when you start increasing the number of moles of gas quite a bit, or increasing the pressure quite a bit, right? If you increase the density of that gas, all of a sudden there's way more collisions, and that becomes a much bigger, way more gas particles, and that becomes a much bigger deviation from ideal behavior, all right? So in general, what you'll see is deviations from ideal behavior only happen for really concentrated gas samples, okay? So then let's do another one, and we'll just like crank up the crap out of how much gas is in there, all right? We'll use our pressure formula here. Yeah. I'll just rewrite it here. What is the corrected pressure? For xenon. For 1 mole of, no, not 1. We're going to make it 40 moles of xenon. And 5 liters at 25 degrees Celsius. All right, if we want the pressure, we're going to use our pressure correction. Oh, this isn't going to work. We might have picked too extreme of an example here. Yeah. Okay. All right. This was a little crazy of an example. I guess you really just are not going to be able to get xenon to be quite that compressed, because now we get a negative pressure, which is not really going to happen. All right. So I guess I tried to go extreme to try to prove how much of a deviation this was going to be from the real gas law. But I think I went a little too extreme. So let's dial this back and say we're talking about just 4 moles. could break it. Oh, I gotta look into that. All right. All right. All right, so we get a real pressure of 17.4916. Again, we're just going to say 3 sig figs. If we had done the ideal gas law with any sort of pressure or with any sort of pressure or volume correction, we would have gotten 19.57 to ATM. All right, so now we have a concentrated enough gas sample for which our real gas law deviates quite a bit from our ideal gas law. And again, I guess we can even crank it up so high that we're going to break this whole equation altogether and we get a negative number. All right. But yeah, so we have our volume correction and our pressure correction all in one in our pressure correction formula here. All right, and so we're going to look up our values on our table that depend on our gas to make our corrections for our real gas law. Okay, and again, just to put it up here so that we're super extra special clear, this is our equation. One thing that I will note, and we've had this quite a bit, you better put that denominator in parentheses over and over again to keep those both in the denominator. So when you punch it into your calculator, you would do nRT divided by, in parentheses, volume minus NB minus A times in parentheses, and then you need yet another set of parentheses for down here. Cool. All right, that's all we got for our discussion of gases. All right, so yeah, we'll do our 15-minute break. Y'all can break until we meet at 7, right?